Hi everybody, this is Cal with section 5.1, Continuous Functions. This section defines what it means for a function to be continuous at a point, and this is a relatively short section, but the material is kind of dense. Some of the concepts here should hopefully be familiar from Calc 1, but in some cases this might be a refresher of what continuity meant in Calc 1. So definition 511 is where your book defines continuity for f at a point C. And you should look at this carefully. Let A be an R, let F be from A to R, let C be a point in A in the domain. We say that f is continuous at C if given any epsilon greater than 0. There is a delta greater than 0, so that if x is any point of A in the domain, satisfying absolute value of x minus c is less than delta, that x is within delta of c, then f of x minus f of c is less than epsilon. And if this fails, then we say f is discontinuous. Now, you should pay careful attention to what this has in common with the definition of the limit as x approaches c of f of x equaling f of c. There are some differences, and it's really important to focus on exactly what those differences are. The first one is that this doesn't say anything about C being a cluster point of A, which means that we're going to have to think about what it means to be continuous at a cluster point and to be continuous not at a cluster point. The other thing is that we don't have, when we're talking about the distance from x to c, we don't have 0 less than absolute value of x minus c less than delta. This means here x is allowed to be equal to c. This actually does take into account what actually happens to f when x equals c. Those are the main differences. So there are some pretty good pictures below. And in Theorem 512, the book gives the neighborhood definition of this concept, which should be relatively straightforward. The remarks starting at the bottom of page 125 are extremely important. Remark 1 gets at what I was just saying about the definition. If C is a cluster point of A, then we have that f is continuous at C if and only if the limit of f as x approaches C is f of C. And this should be familiar from Calc 1. Remark, so at the top of the page, your book goes into the three things that must happen if C is a cluster point for f to be continuous at C, and you learned these in Calc 1. F has to be defined at C so that f of C exists. The limit of f at C must exist, and these two values must be equal. The second remark is really interesting. What happens if C is not a cluster point of A? And I urge you to pay special attention to that case. 513 is a sequential criterion for continuity, and this is just an application of Theorem 418. And 514 is a discontinuity criterion, which again follows the development in Chapter 4. And you should understand these and be familiar with them. Definition 515 talks about continuity on a set, which should make a lot of sense if you understand continuity at a point. And then 516 are examples. The first few of these are really straightforward, and they should be a quick read. You should read them carefully. This gets interesting when we hit part G, and I really urge you to pay close attention. I've used that phrase a couple of times in this video. I urge you to pay close attention to example 516G and 516H, which is on page 128 and has a picture on the previous page. Here's the picture of Thomai's function, which is in part H. These are really cool examples. Thomai's function in H is absolutely great, and you should work your way through that one. Then we have some remarks in 517, and these amount to remarks in what you might have called removable discontinuities in Calc 1. And they're followed immediately by examples in 518. And this is an interesting concept, so do read the remarks carefully and look through the examples. And there's a nice graph of x sine 1 over x, which relates to continuity for that function. So, that's it for section 5.1.